Welcome back. In this next video, we're going to be talking about matrix and vector operations. Up first, we're going to talk about the conjugate transpose. So the conjugate transpose is a more complex variation of the transpose that was introduced in the previous slide, where here you're assuming the matrix has complex entries. And again, just like with the regular transpose from the previous video, you switch the rows and the columns. But here, additionally, you also take the complex conjugate of each entry. So this entry right here, A12, is the complex conjugate, the number with the same real but the opposite imaginary part as that number right there. We also note that transposes can be applied to vectors, and that if you transpose a column vector, it becomes a row vector, and vice versa. The addition of vectors is done in a fairly straightforward manner, where you add them term by term. And notably, in order for this to be well defined, the two matrices must have the same shape. Scalar multiplication, where alpha is a scalar and A is an m by n matrix, can also just be done term by term. For vector-vector products, there are two common choices that we'll be using in this class. They're called the inner product and the outer product. The inner product, which is also sometimes referred to as the dot product, is formally computed by taking x transpose times y, which is equivalent to just taking the jth entry of x, timesing it by the jth entry of y, and then summing over j. Something that's worth noting, though, is that if x and y are complex vectors, then the inner product is actually given by x star y, indicating that you use the conjugate transpose, not the regular transpose. And this is because this will allow for x star x to always be a positive real number, with the one exception being if x is 0, then it'll be 0. The outer product is the other way. So unlike the inner product, which produced a single number, the outer product will yield a matrix. Specifically, if x has length n and y has length m, we're going to get an m by n matrix whose ijth entry is given by xi times yj. And similarly to the inner product, if we're dealing with complex vectors, then there's a conjugation involved. Now, to get to the matrix vector product, we're going to first write it like this, which might be different than another formula you've seen before, which will be reoccurring soon. We're going to say that AX is going to be a linear combination of the columns of A, where it's x1 times the first column plus x2 times the second column plus x3 times the third column, and so forth. And so what this means is that AX is always going to be a linear combination of the columns of A. And we'll also note that the set of all vectors that can be written as a linear combination of the columns of A is referred to as the column space of A. Some other important observations is the only way for this to make sense is if the number of columns in A is equal to the number of rows in X, and then also that the shape AX is going to be in CM. In other words, you're going to input a vector of length n, act on it by an m by n matrix, and get a vector of length m. The other important observation is we also have this formula where BI is the sum of AIJ xj. And what this means is that you can actually think about this as being an inner product, where this is the inner product of x with the ith row of A. From this formula, you can also see that the cost is going to be on the order of m times n. In other words, for square matrices, it'll have quadratic complexity. For matrix-matrix products, we're going to assume that A has shape m by n, B has shape n by p. Notice that this n here has to be equal to that n there. And let B1, B2 up to BP be the columns of B, then the matrix product is defined by giving A times the first column, A times the second column, A times the third column. We know that the number of columns of A must equal the number of rows in P. The shape of B is going to be M by P. And importantly, and this is a bit subtle, usually speaking, A times B does not equal B times A. Additionally, similar to before, we note that we can write CIK to be the sum over J of AIJ, BJK. So what this means is that CIK is just the inner product, the dot product of the ith row of A with the kth column of B. Furthermore, if we count the number of multiplications and additions, we can see that the cost is cubic. So if every matrix was n by n, this would be scaling like n cubed. And in general, it scales like m times n times p. Additionally, we're also going to note an identity for the transpose, which is AB transpose is equal to B transpose times A transpose. And a good little exercise is to look at the shapes of everything going on here and the shapes of everything going on there and verify that this equation appears to make sense. So that's it for this video. Up next will be linear systems.